All right, everybody, we'll go ahead and get started in about 2 or 3 minutes here. If somebody can click the raise hand button that's on the GoToWebinar little control there, I would very much appreciate it. I just want to make sure that there isn't any issue with my sound going through, and I do see that we have a couple hands raised, so I appreciate that. So we'll go ahead and get started in 2 or 3 minutes here. Okay, so it is time to go ahead and get started here. So I want to thank everybody for attending this morning or this afternoon or evening, wherever you are. My name is Martin Beziner. I'm the president and CTO at Staties. And today I'm going to be giving a very, very short crash course in the mixture design of experiments. Okay. So this is part of a series of short crash courses that we do. We have one for response surface designs. We have one just for general design of experiments, but this one is specifically focused on formulation design of experiments, or DOE. Okay, so just a little preliminary here. We have a decent turnout today. Okay, so to avoid any audio disruptions, I'm going to mute all of the attendees here. Okay, there is a questions area in the GoToWebinar tool where you can type in questions as they come up. Okay, I'll try to get to them throughout the webinar as there's kind of breaks that crop up. If not, feel free to email this address here, stathelp@staties.com. Okay, and we will try to get to them afterwards and get back to you then. Okay, so this email address right here. Okay, and also if you need to leave early, or if there's something that you didn't catch, or if there's something that you'd like to rewatch or maybe go through again at your own leisure, we will be posting this webinar, the slides and the video, both on our website and on YouTube, on our YouTube channel. So this should be up later today or sometime tomorrow. Okay, so what I'm going to do is, right before we get started, since we are getting to since we are going to get started here now, if I could get one more raise hand from a couple people, just to make sure that people are hearing me. Okay, I got 2, 3. Okay, looks like we're all good to go. So there was once a webinar that we gave, and 10 minutes in, the presenter realized that nobody can hear him and everybody had signed off. So we want to avoid that situation from happening here. So just some latest news from Staties, in case if you're interested. We did release the newest version of Design Expert 13. Okay, and this is a really good release. So this was released January 4th of this year. For anybody that's on a subscription or an annual network license, you can upgrade for free. Okay, and at the very end of this crash course, I'm just going to demo 2 features that are useful for mixture data, for both setting up mixture experiments and analyzing them. So at the end of the crash course, I'll give a little demo on some of the features that are useful for mixture DOE. Unfortunately, we only have about 45 or 50 minutes this morning, but if you'd like basically a 4-day version of this webinar, we do also offer a live web mixture DOE workshop. So this is instructor-led. It's, you'll learn how to use our software Design Expert along with it. And it's, I believe, 4 or 5 half-day sessions of 3.5 hours. And our next one is coming up on May 17th through 20th. So feel free to check that out if you really want to deep dive into mixture experiments, more than just what we can do in this 45 minutes here. Okay, so with that, let's get right into it. So first, I'm going to be talking about what is a mixture experiment, and this is actually a very common question that we get. A lot of experimenters, engineers, chemists, anybody doing R&D are actually often confused. Are they doing a mixture? Are they not? Should they be using mixture DOE? Should they be using a factorial? So that's the first thing we're going to talk about. Then I'll go through the 2 main designs that you can use for mixture experiments. And I'll also do a demo of an analysis of the setup and the analysis of a mixture experiment. Afterwards, the section 3 are some just kind of practical tips and tricks. So if you already have a little bit of knowledge on mixture DOE, hopefully you can get some good information out of this 3rd section here, where we'll be talking more about practical stuff. And then finally, I'll kind of wrap it up. And then, for those of you that want to stay, you can take a look at some of the useful mixture DOE features that we have in the new version of our software. So the very first question is what is a mixture experiment and why do we care? Well, here's what a typical non-mixture experiment looks like. So we're going to kind of start with what you're familiar with. So suppose we're baking a cake, and we're interested in moist cake. So what we're measuring is the moisture content of the cake. And in order to kind of try to see how we can play with the moisture, what we do is we vary the time in the oven from 20 to 30 minutes and the temperature in the oven from 300 to 450 degrees Fahrenheit. Okay, so we make a cake, we make some cake batter, we choose a time and a temperature in the oven, we put it in, we bake it, we take out the cake, and then we measure its moisture content. Notice that in this experiment, both of our factors, which is time and temperature, can be set independently of one another. So in other words, if we decide to set the time, a time of 25 minutes, temperature can still be set to anything from 30 to 450 degrees Fahrenheit. Okay, now this is a very typical response surface experiment because you have factors that vary independently of one another. Okay, you have numeric factors, time and temperature are both numeric. So this is kind of our standard DOE that maybe you've been doing up to this point. So here's what a response surface DOE would look like. So you would see that you would have a column for your time, you'd have a column for your temperature, and then you'd go to the lab or to the kitchen or whatever, experiment and fill in these moisture responses here. And if I were to visualize the time and temperature combinations that I want to run, it would look something like this. You can see that I have time along this axis, I have temperature here, and you could kind of see how the space is filled. Some of these points I might replicate, so I might do more than once, like this one. But as you notice, time and temperature can basically be set independently of one another. Okay. Okay, so now, where does a mixture experiment come in? Okay, now let's consider this following experiment. Now, I do apologize for the slightly simple examples, but since we have people from so many industries here, I tried to choose something that everybody could understand so we could just focus on the DOE without having to worry too much about the subject matter. But suppose, I love my frozen cheese pizzas. And suppose what we're doing is we're deciding what cheese to put on a frozen pizza. Okay. What we could do is we could blend together 3 cheeses, mozzarella, provolone, and white cheddar. So what we do is we take, some proportion of mozzarella, some proportion of provolone, some proportion of white cheddar. We kind of mix it up and we put it on our pizza. So we could try various combinations of the 3 cheeses. Each pizza that we cook, however, will be topped with a total of 6 ounces of cheese. So notice here how there's this word total. And for the 3 things that we're varying, there's a total. So, for example, mozzarella could go from 0 to 6 ounces. Provolone can go from 0 to 6 ounces. White cheddar can go from 0 to 6 ounces. However, mozzarella plus provolone plus white cheddar equals 6 ounces. This is a mixture. Why? Because we have a fixed total. We have this equal sign here, which says that at every run, for every pizza we're making, the sum of all the things that we're mixing together has to stay the same. So as an example, if you put 6 ounces of mozzarella cheese on the pizza, you will be putting 0 ounces of provolone and 0 ounces of white cheddar on there, because that's the only way you can get a total of 6 ounces. Okay, so this is, again, really the key to be on the lookout for is, do you have this equal sign here somewhere? So the responses that we measure will be the appearance, the taste, the texture. Is the cheese blend soft and oozy and creamy, or is it hard and chewy? And then also the cost function, because not every cheese might cost the exact same. Now, in this situation, the components, as we call them, because they're components of a blend or they're components of a mixture, they cannot be set independently of one another. As an example, if we put 2 ounces of mozzarella cheese, we must put 4 ounces of the other 2 cheeses in the blend. Okay, this is a typical mixture experiment here. So this is just a recap of the previous slide, that every run you're going to do, every batch you're going to do, every cheese blend you're going to make adds up to 6 ounces here. So notice in our previous example, when we had time and temperature, there was no equals constraint where time plus temperature had to equal 600. It didn't really make sense in the previous example that I talked about. So here's what a typical mixture DOE would look like. So if you pull out Design Expert, you fired it up, you set up a DOE, it would tell you run number 1. You're not putting in any mozzarella cheese, but you're putting in 3 ounces of provolone and you're putting in 3 ounces of white cheddar. So total 6. Cheese blend number 2. So then what you would do is you'd make up the blend, you'd put it on a pizza, you'd bake the pizza, and then you'd measure your 4 responses: appearance, taste, texture, and then cost is kind of a separate thing. Then what you do is you'd formulate a blend of cheese that had 4 ounces of mozzarella here, 1 ounce of provolone, and 1 ounce of white cheddar. And then you'd put it in the oven, you'd bake it, and you'd measure, the appearance, the taste, and the texture. And so notice that in each row here, as we go, for each row represents a run or a pizza, the sum of the 3 cheeses equals 6. Okay. So again, this is what really makes a mixture experiment. So if I want to look at what my component, what my DOE looks like in mixture space, I'm now, I have 3 components, so I need to be in a 3D space. So if I take this experiment on the previous slide, this DOE here, okay, and I just try to graph it, it's going to look like this guy right here. Okay, and you notice something interesting. You notice that if you were to rotate this graph here, okay, which we can't do easily on PowerPoint, but if you were to rotate it, you'd see that all of the green points, which represent pizzas, which represent the runs, are all on a flat plane. Okay, the reason is even though we have 3 components, the third component is kind of almost useless to a certain extent, because the third component is only added to get a total of 6 ounces. So what I can do is I can kind of, on this side here, I can draw a triangle through this area. And what I would see is that all of the green points or the experimental runs lie, they lay on this triangle. Okay, so really, even though I have 3 components, I only have 2 dimensions because of the fact that I'm only really varying 2 of the components. The third one is added to get the total of 6 ounces here. So instead of looking at this in 3D space, I can simply take this triangle here and make it, kind of flatten it out a little. So this is what I end up getting if I take this triangle and I kind of just, rip it out from this 3D space and I put it flat on the ground. This is what I end up getting. Okay. So if you've ever seen mixtures, if you've already seen a mixture DOE visualized, you'll know that it's not typically done in a square space. It's done in these triangular simplex spaces. Now, in this case, the red points represent the runs. Okay. You could see that the edges here are vertices. These are 1 cheese blends. So in other words, if I'm only putting in 6 ounces of one of the cheeses, so I have 3 vertices, 1 for each cheese. Edges represent blends of 2 cheeses. So I'm blending 2 together, I'm leaving 1 out. Okay, and then any point in the interior here, okay, represents a blend of 3 cheeses. And then you could also see that lots of times, there will be replicates, meaning do the same blend independently 2 or 3 times. Okay. All right, so hopefully that's clear. But this is really the key difference. If we were doing an RSM experiment, a response surface, or a factorial, we would be working in this square space. Because we're doing a mixture, we're working in this triangular space here. All right. So this is kind of the take-home message in identifying whether you need a mixture experiment or not. Blending experiments should usually be set up as a mixture DOE, okay, but not necessarily always. Here's kind of one exemption. If you are varying concentration or the amounts of components, so for example, instead of going from volume percent or weight percent, you're going from how many liters of something you're putting in, where the amount is not fixed, or the concentrations, where typically you don't sum up the concentrations to a fixed total. In a situation like that, you may need to still use a response surface experiment. Okay, but if you're working on a weight percent or volume percent or a proportion of total scale here, you most likely have a mixture experiment. So the key to verifying, this is probably the most important bullet of this section, is the key to verifying whether you need a mixture design is to determine if any of the columns in the design plan, if they add up to a fixed total in each run of the experiment, okay? If they don't add up to a fixed total, you don't have a mixture experiment. Now, here's kind of another little caveat that, again, we unfortunately don't have much time to talk about, but you may often have part of an experiment be a mixture, something like a cake batter formulation where it's always a fixed volume or weight. And you may also have non-mixture factors as well, like the temperature of the oven. This is called a mixture process design. And unfortunately, we have no time today to get into those, but we will do something in the future. So if you are formulating, but then you're also processing the formulation under a bunch of different conditions, then you have a mixture process design, combined design. It's still a mixture design, but it's kind of, mixture design plus more. Okay, so I'm going to go ahead and just briefly pause just to see if any questions came in, and I don't think any have yet. So what we could do is we can go on to talking about what do mixture designs actually look like and what are the 2 major categories of them. Okay, so this is actually pretty simple. There are 2 basic categories of mixture DOEs. You have these simplex-based designs, which are what we call them canned designs or off-the-shelf designs, because they're basically pre-generated and you just use them for your problem. And then we also have optimal computer-generated designs. In practice, most of the designs that personally I use, and I've used in the last 8 to 10 years, I would say 99% of the time I use these optimal designs, okay, because they're way more flexible and they're way more practical. So I'm just going to show you what a simplex design looks like, but we're not going to actually ever use it. I mean, I use them very, very little. So simplex designs are canned, and they're very straightforward. However, here's kind of the caveat. In order to use a simplex design, one of the following conditions need to hold true. So all the components that you're blending together have ranges 0 to 100%. Now, if I'm making a cake batter formulation, I mean, does it make sense that butter can go up to 100% of the total formulation? No. Or, if I have a reaction, does it make sense that catalyst, should take a lower bound of 0? The answer is probably not. So all of the components have ranges 0 to 100%. That's one of the conditions that means you can use a simplex lattice design. Second case where you could use it is if all of the components have the same range. So if you have a situation where component A goes from 1 to 5, component B goes from 10 through 14, and component C goes from 96 to 100. Okay, all of these have a range of 4. In that situation, you can also use a simplex lattice design. Again, this is pretty rare. I mean, it's pretty rare that I've run into something like this over the years. I would definitely not try to force your components to have the same range. Maybe expand some of the ranges or shrink some of the ranges so that you could use these designs. Which is why we're gonna use optimal designs. And simplex lattice designs look something like this. They're nice, triangular, everything is evenly spaced, everything looks really nice. This is a 3-component design. This one here on the right is a 4-component design. Okay, so I think enough said on that topic. So simplex designs, as I said, are incredibly restrictive and limited purpose. Rarely makes sense for all components to go from 0 to 100% of the mixture. I mean, does 100% yeast in a bread dough formulation make sense? No. And it's also somewhat, I mean, this should probably say very rare that all the components have exactly the same range. And as I said before, don't force all of your components to have the same range so that you could use a simplex design. A better solution is an optimal computer-generated design. Now, if you open up Design Expert and you click on New Design, this is where you will find, if you do want to use a simplex design, this is where you'll find it. You'll find it in the mixture section, and it's the first one. It's the simplex design. Okay. Now, here's a more realistic example. Suppose you have the following set of constraints. You have, 3 components that you're blending together, and let's say that A goes from 0 to 20%, B goes from 0 to 50%, C goes from 0 to 50%. However, A plus B also needs to be at least 10%. So in other words, I can't have components A and B both be 0. And also, the ratio of components B to C needs to be between 1 and 1.5. And there's this equality constraint that says that A plus B plus C needs to equal 100%. So if you were to set this up in Design Expert, you would go ahead and enter your single component constraints here. You'd click on this Edit Constraints button, and you'd enter your multi-component constraints here. These problems can get incredibly convoluted because there's usually lots of constraints involving more than one component, ratios, sums, differences, if-then types of things. So here's what the design space for this experiment that I just showed looks like. This triangle here is that full 0 to 100% simplex, although I've changed it to go from 0 to 1. Okay, so you could see that this white region here is the region that satisfies all of these constraints I had here on the previous page. All of that boils down to this little white region here, this little, I guess, 1, 2, 3, 4-sided figure here. Okay, so notice that in this 0 to 100% space, I'm only experimenting in a tiny little region here. And what I did here is I basically took my magnifying glass and I zoomed in on this, I kind of drew a triangle around this and I zoomed in here so that it's a little easier to see. So as you can see, this white region is clearly not a great fit for trying to use one of those triangular simplex-based designs, okay? And definitely don't, change your problem so that, oh, you can work in this triangle here, okay? This is the reason why we have optimal designs. So here is what an optimal computer-generated design looks like for this complicated design space here, okay? So you'd go ahead, you'd set up your lower and your upper bounds and all of your constraints, and then Design Expert using an optimal design would generate something that looks like this. So you could see that the red points are where you do runs. You could see that, Design Expert suggests some replicates here. Okay, you're doing lots of points on the edges, but you're also doing quite a few points here in the interior. And that's basically it. And we'll talk about, how to set this up here in just a minute. But this is what I would say 99% of the experiments that I set up look like. They're optimal designs. They're very complicated design spaces, lots of crazy constraints and whatnot. So, we'll dig a little bit deeper into this. Optimal designs, they're very straightforward to build. Okay. So if you're working in Design Expert, you'd go to, you'd click on New Design, and then you'd see that there's this Optimal tab here that you can click on. So what you need to do is you need to choose the components. This is a subject matter question. You need to set their upper and their lower bounds. And then you need to figure out if there are any constraints that involve more than one component. So if I go to this screenshot here, this is a 4-component example. Note the only difference between mixtures and other types of experiments is that you have this total field here. Okay, so then what you do is you type in your factor names, you type in their lower and their upper bounds. And then if you have any constraints like A plus B is less than 0.3, or the ratio of B to C needs to be at least 1.3, you deal with that in this Edit Constraints button here. Okay, so hopefully that's clear. Then what you do is you need to choose the design size, meaning how many runs you can perform. What types of runs will go into the design? Do you need blocks? What type of model are you interested in fitting, and so on. So this is a summary of what goes on, and I'm going to go through the build process here in just a minute. This is kind of the whole, this is what the build process looks like. So as you can see here, this is an optimal design. Requires 10 runs if I want to fit a quadratic model to fit curvature in the data. 5 space filling points, 5 replicates. Okay, and I'm like, as I said, I'm going to go through this in just a second here. So this is essentially what the process looks like to get that red design that we built. So now what I'll do is I'll actually go through an example of how to build a design, analyze the data and build a model, and how to optimize the formulation. Okay, so we'll go back to the pizza cheese blend example and use the following components and bounds. So what we're going to do, and this was an actual experiment that we had done, was we were going to have mozzarella go from 2 to 6 ounces, provolone go from 1 to 4 ounces, and white cheddar go from 0 to 2 ounces, and we're still going to put a total of 6 ounces of cheese on each pizza. That seems a little low to me. I think, you know, it should be a lot more, but anyways, that was what was done. Okay, so I'm gonna go ahead and just switch over to the software here so you could see how this is done. Okay, so I'm gonna click on my new design here, and I know I'm working in the mixture area, so I'm gonna go ahead and click on mixtures here. Okay. Now I'm going to go ahead, and what I could try to do if I wanted to is I could try to set this up as a simplex lattice design. I'll say my total is 6 ounces here. Mozzarella goes from 2 to 6. Provolone goes from 1 to 4. And then white cheddar goes from 0 to 2. Okay. Now, let's say I try to click next. Design Expert first is going to complain that my bounds don't make sense. Okay, it's going to say that there's absolutely no way to put in 6 ounces of mozzarella cheese if provolone has to be at least 1. Okay, so notice how what it's going to do is it's going to try to adjust the ranges for me. And if I click on OK, I'm going to accept that. Okay, but now I get a warning from Design Expert that says because of the bounds you have selected or constraints you may have entered, your mixture space is no longer a simplex. Would you like to switch to an optimal design and continue with your current ranges and constraints? Basically, Design Expert says that you can't be using one of those simplex designs here. So it'll say, do you want to just move to the optimal design with what you typed in? I'm going to click yes, but if you really were dead set on using a simplex design, which you shouldn't be, you would click on no, and then you'd have to manually adjust your ranges. So I'm going to click on yes, and now I am in the optimal design. Now remember, I had an upper bound of 6 here for mozzarella, and Design Expert complained. Design Expert is going to always check the bounds for consistency to make sure that all of the runs can actually be done. And it's going to offer you, you know, if it detects any problems here, like having a, you know, a maximum mozzarella of 6 and a minimum provolone of 1, that says that if the provolone is, you know, has to be 1, then mozzarella cannot be 6. What it's going to do is knock down the upper bounds. So what you need to do is you need to take a look at this, okay, because people almost always get these ranges wrong on the first time through, because it's really hard to kind of go through this when you have tons and tons of components. You need to look at this and see if it makes sense. Are you okay with mozzarella going down to 5? If you are in a situation where you absolutely need mozzarella to go up to 6, then what you need to do is manually change the lower bound of provolone to 0. So you need to give this a little thought. I'm going to click OK. I'm okay with going up to 5 ounces of, or we were okay with going up to only 5 ounces of mozzarella. And then this is where you would choose how to actually build the design. So I'm going for a quadratic model, meaning I want to be able to fit curvature in the data. I need to do at least 6 runs, and then I'm going to add 5 lack of fit points and 5 replicates. So in other words, I'm going to do 5 of the blends twice. Doing replicates is critical because it gives you an idea of how much kind of natural variability there is in your process. If you do the same point 2 or 3 times, you know, in theory, you should get exactly the same measurement, but you know, that doesn't happen very often. Okay, so what this would do is tell you how much variability is there in your process. And then I'm going to go ahead and click finish and then let Design Expert build the design. And I'm going to go ahead and actually open the design that we used, which has the taste score in here and has the runs that we actually did. Okay, so what would happen is that this column would be blank, and then you'd go through and you'd need to make 16 pizzas and then just measure the taste. This was a score, I think it was on a scale of 0 to 100 for 3. It was an average, I think, of 3 or 5 people for each one of these. This was done so many years ago that I don't remember the exact details, but it is what it is. So now, again, since we don't have a ton of time, I'm going to go ahead and just show you what an analysis would look like. So we would go to taste. We want to kind of see how are the different cheeses interacting with one another to affect the taste, and what is the blend that gives me the highest expected taste. So I'm going to go ahead and click on Start Analysis here. Fit Summary suggests a quadratic model, which means there's probably some curvature in my data. I'm going to look at the ANOVA, which tells me, okay, there's lots of, lots of nonlinear blending that's going on. Lack of fit is not significant, so this model, it doesn't appear that there's any signal that's being lost here in the model. Okay. I would go through and check my diagnostics. Notice here how I have one point that looks like it's sticking out. Okay, so what I would do is probably if I were working with somebody, I would go and go back and ask them, hey, what happened at this pizza? Is this really an outlier of some sort? Was this a typo? Does it make sense that the taste of the pizza, the taste score can be 175 under these conditions? And we have lots of webinars and resources on how to deal with problematic data. So unfortunately, this is all I can say for now. But then when I look at the graph, I can see this is my DOE space here, and I can see that if I want the highest taste score, okay, I probably want to be at, let's see here, mozzarella of about 3, provolone at its lower bound of 1, and lots of white cheddar at its upper bound. I could also use the numerical optimization to click on taste here and maximize taste. Okay. And I can see that my best solution occurs when mozzarella is at 3, provolone is at its lower bound, white cheddar is at its upper bound. So perhaps if I were to do this experiment again, maybe I would lower the amount of provolone, maybe put the lower bound at 0, see if I can just omit provolone and maybe let white cheddar go up to something like 3%. And then I get my graphs here. So that was a quick 5-minute whirlwind tour of how to set up and analyze these types of designs. And of course, you may have multiple responses: taste, texture, appearance. You may have a cost function where you also want to take into account the cost of the cheeses, because maybe perhaps white cheddar is 3 times as expensive as mozzarella, so you might not want to put too much of that in. So there's lots and lots of stuff that we do go into detail in our live web workshop. We also do have lots of free resources on our website and on our YouTube channel, so feel free to check that out. But unfortunately, this is we're gonna have to move on from this example now so that we could finish up the rest here. But hopefully that at least gave you some flavor of how this is done. Okay, so this next section here is just practical tips and tricks. So these are kind of common errors that we see people make. Maybe suggestions that are better than what your academic textbooks will tell you to do. So that's what we'll do. That's what I'll do now. So here is a summary of a few tips and tricks here that might be helpful to you. First of all, lots of mixture textbooks and even other short courses will say, oh, you could, see if a factorial design will work in your situation. My suggestion is don't use factorial designs. Just if you're in a mixture situation, don't try to force another type of design into your problem. Second tip and trick is don't convert, lots of people, and I've seen people with master's degrees in statistics do this. Well, they'll say, well, we have a mixture experiment, so why don't you just convert to ratios, and then you can use a factorial or a response surface design. My suggestion is don't do that. I think it's a really bad idea for the most part, except in a few special cases. If you're going to start a mixture DOE, spend a lot of time choosing the components that you're going to vary and their ranges. By far, the biggest source of failures in mixture DOEs is, in my experience, is choosing the wrong bounds. So you're experimenting in the wrong region of the space, the design space. Maybe one of your components had a range that was too narrow, one that was too wide. So spend a ton of time choosing, because 90% of the success is going to depend on, are you experimenting in the right space? And with mixtures, it's tricky because not everything varies independently. So if you want to put in more water, you might have to take out, you might have to put in less of some other component. Experiment iteratively, especially in new problems. And then finally, master building optimal design. So I'm going to go through each of these, a slide or two on each of these. So don't use factorial designs, just don't do it. Here's something that you'll constantly see, academic textbooks, saying to do. They'll say, oh, okay, component A, B, and C go from 0 to 100%, or 0 to 10%, sorry. And then component D is a filler, and it basically serves just to bring the total up to 100%. So something like water is a typical filler. So what textbooks will do, or they'll suggest, ignore component D, and perform a 2 to the 3 factorial design on components A, B, and C. Now this design has two, this approach I think has two huge issues. First of all, the design is poor. It's very bad, since what you're doing is you're only looking, a factorial design will typically only look at the highs and lows. So you're only going to be looking at the extremes of each factor ranges. So you're basically just going to be testing component A at 0 and component A at 10%, component B at 0, component B at 10%. Second of all, when you go and do the modeling, the assumption that's made is typically is that D is inert, meaning D doesn't really participate in the, in the reaction of whatever. It doesn't have any. If it turns out that the quote unquote filler component actually does have an active effect, then the model that you build is going to be misleading. Okay, you're going to basically have something called aliasing, where the effect of component D is kind of distributed in the effects of A, B, and C. So what you're seeing going on with A in the model might actually be some combination of A and D, and you never know that. So, and here's kind of another, just a little comparison here. Here is a 4-component optimal design. Okay, notice here how this is not a particularly complicated design. It still has this quote unquote filler component. It's 10 runs, but notice how I have points in the middle here. I have edges. I have some points in the interior, like at run number 4. If you built this factorial design ignoring component D, you'd have a design that looks like this. First of all, D is gone because we're assuming, we're dropping it. But also you could see that you're literally only testing the extremes. You're testing each component basically whether it's at 10 or whether it's at 0. So you're losing information about, the nonlinear blending properties here. So you're saving 2 runs because of the assumption that D doesn't matter. But if D does matter, then I think, I think you're in trouble here. So to me, it's safer to just use this mixture design. Okay, you're doing 2 more runs. You're getting the, the correct effect estimates. You're getting estimates of nonlinear blending. For example, is there a hump in the middle of the space? Is there a valley in the middle of the space? So I don't like this approach. I personally think it, probably shouldn't be taught, but I mean, it is. So I like to at least say, hey, maybe think twice if you're going to use it. Tip number 2, don't use ratios so that you can use factorial or response surface designs. Now, there's a caveat here. If kind of the problem is better defined on a ratio scale, or if, scientifically it really does make sense to look at ratios, then that's fine. It's perfectly fine to use ratios in that case. But I'm talking about starting with, a problem that's naturally defined on a weight percent or volume scale, and then changing everything to a ratio so that you could use a factorial design or a response surface design. So To avoid using mixture DOE and to overcome the limitation of factorial designs in the previous tip, experimenters will often convert their mixture problem to a ratio problem. So here's what it looks like. Let's say you had 3 components, A, B, and C. What you can do is you can create a 2-factor response surface design by, instead of looking at A, B, and C, you look at the ratio of A to C and the ratio of B to C. Okay, so first of all, notice immediately, because C is in the denominator, you can't have C go to 0. So if all of your components have a lower bound of 0, then this doesn't work. Okay, and in fact, the closer you try to get to 0, if you try to make it, something like 10 to the negative 20th, then these ratios are just going to blow up. So you can see there's already one case where this doesn't work, and you would need a mixture design. So in my experience, this is usually a terrible idea, bad idea. So first of all, this approach produces poor design. So if you convert the ratios back to mixture components later on, you'll see that you get these really weird, wacky designs that don't fill the space particularly well. I also find this approach to be incredibly tedious because it requires, you need to go from the volume percents to the ratios, then you need to do the DOE on the ratio scale, but then at the end of the day, when I actually want to go and create my final formulation, I need to back convert to the percent scale. So I find this to be tedious personally. And once again, it may produce models that are misleading. Okay, so I really don't like this approach, but you may see it here and there. And again, I just as a caveat, I only don't like this approach when you're trying to use it to, to force a mixture problem into a response surface design. If you naturally have a ratio problem, that's a different story. Okay, tip number 3 is to spend a lot of time choosing the components and the ranges. The first step in any mixture experiment is choosing what you're going to be blending and what the upper and lower bounds are for each component. And again, as I mentioned this before, this is absolutely critical. Most of the failures of an experiment to produce results are choosing the wrong mixture components and or the wrong bounds. And unfortunately, this is not really a statistical question. Components and their bounds are usually chosen using subject matter knowledge, historical data, and sometimes just, giving it your best guess. And mixtures are especially difficult because of the equality constraints. So if you want, component A to have a narrower range, that means you need to expand the range of another component. And if you have 8 other components, which one do you choose? So this is really where it can get tedious and tricky. So here's, something, this is just a little demonstration of what I often see happening. This is the triangle of truth, meaning, if we knew what was happening behind the scenes. What often happens is that, when people are experimenting, what they'll do is they'll do, a DOE in this region here, and then they'll see that they get absolutely no results. Okay, they just get a flat surface, nothing really going on, whereas they really, had they known the truth, they should have experimented over here. Okay, now of course, you're not going to know this ahead of time, but this is more of just an illustration of what happens more often than not. So really give it a lot, spend a lot of time trying to figure out where the correct place to experiment is. And a lot of times, you're not going to get it right the first time. It's very, very frequent that people will whiff and kind of realize that they got the bounds wrong. But now, tip number 4 ties into that situation. Consider an iterative approach, because you're not necessarily going to get things right on the first pass. So unfortunately, textbooks will often present design of experiments as kind of a one-shot approach, meaning you have a budget of 30 runs, you set up your experiment, you do 30 runs, and that's it. Again, in the real world, more often than not, people wish they had done something differently. So here's how it's often presented. Perform the experiment, build the experiment, perform the experiment, analyze the data, and go home. This is, a fantasy in most situations. Instead of using your entire run budget on the first pass through, why not? So for example, if you're able to do 30 runs, Why not use 20 of them on the first pass through of the experiment and then see what you get? Maybe you'll realize that, oh, one of your components should have been, higher, or one of your components should have been lower. So if you have the luxury to do this, use a fraction of the runs and leave some behind. After you do your smaller preliminary experiment, you could choose what to do with the remaining runs. For example, you might want to expand the mixture space and put the remaining runs in the new area to kind of better optimize the process. You might want to shrink the mixture space and put the remaining runs in a smaller area where you want more precision. Maybe you set up the experiment for a quadratic model, but you realize, oh, you know what, I really should have had a cubic model. You could use the runs to estimate higher order models. Or you could just keep the original space and put the remaining runs, to plug in any large gaps. So notice how, after you have your preliminary results, you could choose what to do to perhaps get a better result going forward. So, and this is not often taught. And in our new version of Design Expert 13, it's very easy now to modify the design space after you've done an experiment. So you could expand the space and put runs there, or you could shrink the space. So all of this can be done easily in Design Expert. And this is here it is. It's Augment Design. You can see that you have a modify design space option now. This was not available in Design Expert 12. And if you'd like more information just on this tip, there's a whole 50-minute webinar that I did some, maybe 6 to 8 months ago that just talks about this one tip number 4. So you can feel free to go ahead and watch that. It's very accessible. It's not, there's not a lot of math. It's more of just strategies that you could be using. And then finally, the last tip here is to master building optimal computer generated designs. Once you've gone through a few of them, it should be pretty straightforward. And as I said, most of the designs you'll build will probably be optimal computer generated designs. Even in situations where a canned Simplex design can be used, it might be better to use an optimal design. So learning the ins and outs of these designs will pay huge dividends going forward. And here is a free video on our YouTube channel about building and analyzing optimal mixture designs. Here's an advanced webinar that we did, and this will of course be available on the slides that we're posting tomorrow. Here is an advanced webinar on using optimal designs. And then finally, if you're interested in getting training, you can go to our training page and see if there's a workshop that might work for you. So I'm going to go ahead and wrap up here, and then I'm going to show 2 features in Design Expert 13 that are super useful for mixtures, only those. So Mixture DOE is a very powerful tool that unfortunately doesn't receive much attention. In fact, when I was getting my PhD in statistics, I never was once exposed to a mixture experiment, not until I started working in the field, so to speak. Design Expert software contains all the latest and greatest tools for building and analyzing mixture experiment. The key to recognizing, do I need a mixture experiment, is to figure out whether you have this equality constraint. Do each of my rows need to sum up to the same total? Okay. And finally, if you enjoyed this presentation and find it useful, you could consider taking our 4-day distance learning workshop that dives into huge amounts of detail and goes through all of this in the software on all of the topics that I discussed. So optimal designs, optimization, building models, evaluating designs, comparing them. There's only so much we could do in these 50 minutes here. So unfortunately, we're going to have to leave it at that. So, and here are just a few resources that we have available. This book here, which I recommend buying on Amazon if you want, is kind of the Bible, so to speak, of DOE for mixtures. It's very academic, very technical, so we don't usually recommend it unless somebody really wants to know the ins and outs. This is a book that we wrote here, which is also available on Amazon. This is Formulation Simplified, which is more of a targeted for engineers and scientists and students and whatnot. And then this is, of course, on our website, the Mixture DOE workshop that we're offering in May. Okay. So with that, that pretty much concludes the main portion of the webinar. And I'm just going to spend 5 minutes for those of you that stick around just to show you a couple new features in Design Expert version 13 that are really helpful for mixtures. So this is an exclusive preview. So as I said, this was just released in January 4th of 2021. If you are on an annual license, you should have gotten an email that you're eligible to upgrade for free. There are many, many new user requested features that we put in. Modified design space wizard. So as I talked to you, remember when I talked about iterative experimentation, this wizard makes it easier to do that. And then we have a round columns feature. A couple other features, Poisson regression, multiple analyses, and a ton of other things. But I'm just going to show this modified design space wizard and this round columns feature. So if you've built a DOE and you did the experiment and you realize, oh, you know what, my space was wrong. It should have been bigger. Maybe one component should have had a bigger range. One component should have had a narrower range. The augment design feature allows you to basically add more runs to the experiment you already did to get better results. A lot of times people will throw away what they did and start over. You don't necessarily have to do that. So as you can see here, you know, this is your original experiment, and what you can do is you can shrink the space, you can expand the space, or you can shift the space and simply just add more runs. Okay, and Design Expert will allow you to do that. It'll ask you, you know, what are the new lows and highs? How many runs do you want to add, and so on. And then our second feature, one complaint that we've always gotten is, you know, I build a design, an optimal design, and I get these, you know, values of the components, like in run number 2, there's no way I can measure out 0.496233. You know, I can't get a proportion of that precision. Okay, so we do have this round columns feature now that allows you to basically specify what level of precision you're able to do the experiment at. You know, you know, with what precision can you measure out your components, and then the software will automatically round for you. Okay, so this is a feature that we've, you know, that's been requested for ages, and we finally put it in Design Expert 13. And it's really a big problem with mixtures, because if you have independent components, you could round them off by hand. But in a mixture experiment, you know, if you round one component up, then, you know, how do you round the other 7 components and still maintain the equality constraint, maintain that fixed total for each row? So I encourage you to at least check out the trial for free. If excuse me, as I said, if you're on an annual plan, you can just get this for free. In fact, you should have gotten an emailed upgrade already. And so with that, I want to thank you all for, you know, taking an hour of your morning to listen in. Hopefully, you know, I know this was a ton of information in a short amount of time, but hopefully you at least got kind of a flavor of what mixture DOE is about. That was really the goal here. So once again, this will be posted on YouTube. The slides will be available probably this afternoon. And so yeah, I really encourage you to spend some time on this if you're, you know, interested in mixture DOE. I think, you know, learning the ins and outs of this, or at least getting a good foundation, will pay huge dividends going forward. So with that, I want to thank everybody once again. And if you have any questions, feel free. You could email this address here, or you can email the stat help address I gave you at the beginning. And with that, I think we can go ahead and wrap up. So thanks again, and take care.